2 today. This is day 4. So this is the last day that we're going to go over material. And then Friday is going to exclusively be dedicated for a test. You'll get an announcement email on Friday morning at 7:30 of the testing procedures. Just please make sure that you do your lockdown browser practice quiz, okay? All right, let's go and get started. So, physical applications. A quick recap of these trig functions. We know that from sine to cosine, and then from cosine to negative sine, that these are all just derivatives. While if we go backwards from sine, we get negative cosine, and negative cosine, negative sine, and so on. And these are just integrals. So keep that pattern in mind, just because we're going to do some of these integrals that have these trig functions, and it's just a nice reminder overall. All right, for the for physical applications, we're going to go over 3 of them. First, mass from a linear density function. If a thin rod lies along the x-axis from x equal to a to b, and the linear density, which is the mass per unit length, is given by a function rho of x, this p looking thing is the Greek letter rho, then the total mass of the rod is defined by this integral. So a 10-meter rod has a density of rho of x is equal to 5 plus sine of x. Find the mass. So they want us to plug into this integral for rho of x from a to b. They want us to plug in 5 plus sine of x. Oh, I forgot dx here, excuse me. Dx. Now keep in mind, it's 10 meters. So really, they didn't give us like a start and finish, but we know it's 10 meters. So you can literally pick any point that represents 10 meters. So you can pick 0, 10, 1, 11, 2, 12, and notice that the difference between the two numbers I've been saying is 10. So we're just going to do the easy one, and we're going to do 0 and 10. We do this integral, and we get 5x minus cosine of x from 10 to 0. I'm gonna take advantage of the fact that 0 will just actually wait. We don't know that obviously yet. So let me go ahead and actually do it. And now I'm looking at it, we definitely can do that mistake. Force a habit for the polynomials. We're gonna fill this out when it's 10. So we have 5 times 10, which is 50. And then x is 10, so negative cosine of 10. Do one set parentheses. And then for the other guy, let's see if this color works well. It's silver by... it doesn't look that well. Let's do this one. We have 5 times 0, which is 0. And then minus cosine of 0. Now from this, we can really only mess with this. This just becomes 0. So that'd be a 1. So from this purple, I really don't touch anything. It's just 50 minus cosine of 10. You can't really simplify this. However, this we know is 1. So you're subtracting a negative 1, just plus 1. And that means our final answer is 51 minus cosine of 10. And that's going to be the mass. All right, pretty straightforward. Let's do another application. So this reads mass from a radical density function. If a circular object, like a disk, has a radical density rho of x, its total mass is defined here, where this r stands for the radius, this 2 pi is just a constant, x would be the input, and then rho is provided to us. So a disk of radius 4 meters has a radical density rho of square root of x. Find its total mass. So we're going to take the problem and we're going to plug in all of these individual pieces. Um, it says the radius is 4, so that means that's going to get replaced with a 4. And it says that rho is square root of x. So we have 2 pi x square root of x. From here, I really should just mash these together via my exponent power properties. I'm going to take out the 2 pi, and this would be x to the power of 3 over 2. I keep forgetting the dx. Quick recap on this, just to clarify. When you have a to the power of n times a to the power of m, you can add them to represent one base. And then we know that the square root of a is really just a to the power of 1 over 2. And that the nth root for any n there of a is just a to the power of 1 over n. So 1/2 plus 1 is just 3 over 2. And then that lets us just provide I'm sorry, not 3 over 2. 5 over 2 divided by 5 over 2 from 4 to 0. I'm going to go ahead and before I evaluate this at 4, simply just get out that fraction. So 2 pi and then 2 over 5, because it's a division within a division. X to the power of 5 over 2, 4, 0. And then that can just simplify to 4 pi over 5, x 5 over 2, 4, 0. Now I can take advantage of the fact that plugging in 4 here is going to be some value, but plugging in 0 will just disappear. So I'm just going to take advantage of that. We got 4 pi over 5 is 4 times 4 to the power of 5 over 2. Now, I see here that I technically have two options on how to evaluate this. Assuming you don't have a calculator, or if you, because for the first test, I'm not gonna let you use a calculator. But I know I do enable on Lockdown Browser the scientific calculator, so I'm not sure if that shows up. The square root, I mean. But you have two options for this. You can either do the square root first, and then to the power of 5, or, excuse me, or you can take it to the power of 5 first, and then square root it. Now, I don't like how big of a number this could become, and then only to just square root it. So I'm going to do the easier route, in my opinion, this route. Because I know the square root of 4 is just 2. And 2 to the power of 5, that's going to be, I believe it's 32. Yeah. So 4 pi over 5 times 32. And then that can be written as one big thing. We got 8 pi over 5. And that be your answer. Alright. Next. The last form of application here. Work done by a variable force. If a force f of x, which produces newtons in the newtons n, moves an object from A to B, then work is measured in joules. Hooke's law states an approximation of the response of elastic response of spring-like objects is defined as f of x. Wait, yeah, okay. F of x is equal to k times x, where k is some constant. A spring obeys Hooke's law and requires 10 newtons to stretch it 2 meters. So that means F of 2 is equal to 10. Let me go ahead and just do this a little right here. How much work does it take to stretch it from 0 to 2 meters? And the formula for work is going to be here. So let's go ahead and just plug that in. Oh, wait, we don't know what f of x is. They did not give us f of x, but they gave us a sort of way to figure it out. We know that f of 2 is equal to 10. And we know that technically f of 2 in this general format is just 2k. So 2k is equal to f of 2. And f of 2 is equal to 10. So we could just solve for k by writing it like this. And we can see here that k is just 5. Now we can do the integral from a to b of that f of x dx. It says we moved it from 0 to 2, so the integral will be from 0 to 2. And then we can define f of x as 5x dx. Okay. Then from here, we can go ahead and just, you could take a step and take out the 5. And then you do 5 bracket x squared over 2 from 2 to 0. Taking advantage of the fact that 0 will make the whole thing disappear, you're just going to plug in 2. 5 times 4 over 2, which I technically should have just done. That's going to be 10. And we're measuring work, so work is in joules. Right. So we're obviously there's more to this, and you can keep going further with these sort of physics applications, but this is Cal, so we're not going to stress too much about it. Now, I'm going to tell you right now that I am probably going to pick at least one problem from 2.4 or from 2.5 to appear on your exam. So don't think this is gone. I'm definitely going to pick one of these two application scenarios to appear on your exam tomorrow. So don't count it off just yet. All right, so let's move forward to 2.5, exponential growth and decay. Many natural processes, population growth, money computing, radioactive decay, can be modeled by exponential equations of the form y is equal to y0 e to the kt, where y0 is our initial, I'll say amount because technically it could be used for anything, and then k is our rate. So let's read this. A bacteria culture starts with 500 bacteria and grows at a rate proportional to its size. After 3 hours, the population is 2,000. Find the population